We are doing well and healthy. I'm Mahmoud Khaled, a PhD student from Technical University of Munich. I'm also a research assistant at Ludwig Maximilian Universität München. This work is a joint work with Abul Fazl Lavai from Ludwig Maximilian Universität München, Sadiq Sudiani from Newcastle University, and Majid Zamani from University of Colorado Boulder in USA. AMYTISS is used to automatically design controllers for stochastic systems. Stochastic systems are a general class of dynamical systems with disturbances and noise. They can be used to model several classes of physical systems and applications, including robots and autonomous vehicles. Given high-level specifications like reachability and safety, AMYTISS can automatically generate controllers that are correct by construction and guaranteed to enforce those specifications. Here we are considering discrete time stochastic control systems, and a discrete time stochastic control systems is a tuple. X is a set of states, U is a set of inputs, W is a set of disturbances, and sigma is a sequence of random variables from the sample space omega to a measurable set V. If here is a transition map that takes a state and an input and a disturbance occurrence and then gives us the next state. The evolution of the system is described by a difference equation where a state in the next time is computed by applying the transition map on the current state and input and disturbance plus epsilon, which is representing the noise. Epsilon representing the noise can be an additive noise or can be a multiplicative noise. All the details about the tool AMYTISS, the theory behind it, applications, and case studies can be found in the tool paper of AMYTISS, which is accepted in the International Conference for Computer-Aided Verification, CAV 2020. The main contributions of AMYTISS are: first, we implemented it on top of p-faces, a recently introduced acceleration ecosystem for designing, implementing, and accelerating parallel algorithms. As a kernel on top of p-faces, AMYTISS supports high-performance computing platforms like CPUs, GPUs, hardware accelerators, cloud computing, and supercomputers. And it supports all operating systems. In AMYTISS, we introduced a novel data parallel algorithm for constructing finite Markov decision processes that represent abstractions of those discrete time stochastic control systems. We also proposed parallel algorithms for synthesizing the discrete controllers using the constructed MDPs to satisfy safety specifications, reachability specifications, and reach avoid specifications. As said, AMYTISS design automatically means that you only provide the description of the system and the specification, and with a push button you get the controller automatically. Compared to current state-of-the-art tools, AMYTISS includes new features. For example, AMYTISS supports several platforms like CPUs, GPUs, and hardware accelerators, whereas all current tools support only CPUs. The algorithms in AMYTISS are parallel algorithms, which are meant for scalability and using all available resources. In AMYTISS, we consider nonlinear models, where all other tools consider linear or bilinear systems. In AMYTISS, we consider reach-avoid specifications, not only safety and reachability. We also consider multiplicative noise, not only additive noise. We allow the user to describe the noise with normal, uniform, exponential, beta, or even user-defined distributions. In AMYTISS, parallel algorithms are introduced to design the finite Markov decision processes. An MDE represents an abstraction of the discrete time control system in hand. We construct the MDP in parallel by launching parallel threads over all X U pairs. Having an XU pair, we have a current state and a current applied input. We can compute all possible post states, including disturbances and noise. For disturbances, we consider closed sets representing all possible values of disturbances. For noise, we use the provided distribution. We implemented the controller synthesis as parallel algorithm of the solution to the Bellman equation. Again, all details about the implementation and the theory behind it can be found in the tool paper. We used on-the-fly computation of the transition matrix. So instead of pre-computing the transition matrix, those values that are needed during the synthesis are only computed when they are needed. This reduces the required memory at the cost of repeated computations of the required entries in the transition matrix Tx. This eventually gives the user an additional control over the trade-off between the computation time and the memory usage. The user had the choice to activate those features in the parallel algorithms or use the base parallel algorithms provided inside AMYTISS. In all cases, the parallel algorithms are designed for scalability. This means adding more processing elements to the platform used for the computation will result in improvements in the computation time for the MDPs and the construction of the controller. Here we are considering a 2D robot described by the following difference equation. The next state is a function of the current state, current input, some disturbance, and the noise. The current state and input are living in closed sets as well as the disturbance set. The noise is attached to a normal distribution. We used AMYTISS to design a reach avoid controller. We have a target set described by the blue box and we have an avoid set described by the red box. And we asked AMYTISS to synthesize a controller to enforce this specification, that reaching the target while avoiding the obstacle. Then we simulated the closed loop, means attaching the controller to the system and starting the system with some example initial states. And then starting the simulation and all trajectories of the system can reach the target while avoiding the obstacle. In another example, we asked AMYTISS to design a safety controller, meaning that the state of the system need to stay within some closed set. We call it the safe set. After generating the controller, we simulated the controller for 100 times. During the simulation of this example and the previous reach avoid example, we generate noises using the provided normal distribution of the noise and feed them to the system. As seen in the figure, the controller generated by AMYTISS is able to maintain the system within the provided safe set. We also applied AMYTISS to several benchmarking case studies in order to compare it with other tools and also to test its scalability. We considered many computing platforms, ranging from CPUs in local machines to GPUs in a cloud computing platform called Amazon AWS. The hardware configurations are different in the number of the processing elements. The machine with the highest number of the processing elements is an Amazon cloud machine with an NVIDIA Tesla V100 GPU. It has almost 5,000 processing elements. We propose several benchmarking problems for linear and nonlinear systems and specifications, safety, and reach avoid. The complexity of the problem grows as the size of the system grows. For each of the considered hardware configurations, we ran AMYTISS and collected the computation time. Since the hardware configuration GPU3 has the biggest number of processing elements, it managed to solve the problem in the shortest time. The tools Faust and Stocky failed to solve some of the problems because of lack of memory or because they don't support the considered systems. For example, here, this BMW autonomous vehicle example is a nonlinear system, and both tools do not support linear systems. We computed the speed up of our tool against those tools by comparing the time of GPU 3 against the time required by those tools to solve the problem. The result shows that AMYTISS overperforms all of the considered state-of-the-art tools. Now, let me show you a quick demo of using the tool AMYTISS. You can go to the repository of the tool and it will explain to you how to install the tool. Installation is very easy. Copy the address to the repo and clone it. Now navigate to the cloned repo, and here I assume you have already installed the acceleration ecosystem phases. If not, it will explain how to install it in the repo of AMYTISS. Now you have to build AMYTISS. AMYTISS is a kernel on top of phases, so we use phases to launch AMYTISS as a kernel. Now let's go and run the example we saw in the poster. Examples in AMYTISS are described by configuration file. Here is the configuration file we use to describe this 2D robot and to do reach avoid. Let's have a look to the configuration file. In the configuration file, we give a name to this project. We provide information about the states and the input. We also provide information about the dynamics of the system. Here's the difference equation, information about the noise, and the specification, which is here, reach and avoid. To reach this state, and there is like an avoid hyperrectangle. Now let me check what are the available computing platforms inside this machine by running this simple command from phases. List all CPU and GPU machines. We have here one CPU and two GPU. CPU is device 1 and the last GPU is device 3. Now let us run AMYTISS. We call phases. From the list of CPU and GPU devices, we pick device 1 and the kernel of AMYTISS, and we pass the configuration file, and we ask phases to collect the profiling information. Now we run it. The time taken to solve this problem on the CPU is 46 seconds. If we run the same example on the third device, which is the last GPU in this machine, we will get different computation time. As you see, this GPU is much faster than the CPU, and the problem is solved in much less time. Here I opened MATLAB and navigated to the installation directory, and I go to examples, the example we just computed the controller for, and those are the files storing the controller and the probabilities. We prepared a script in MATLAB script files to simulate the closed loop and show you the probabilities of satisfying the controllers. Here in the closed loop simulation, we just load the controller and start the system at some initial states in the 2D space, and then run the controller and see if it reaches the target and avoid the obstacle or not. Now let's run the simulation. As you can see here, during all those simulations, the controller managed to steer the system to reach the target and avoid the obstacle. Thank you for watching, and I hope you will be using our tool AMYTISS.